The waterproof boots problem is an AP problem that illustrates a couple of important aspects of experimental design. Here's the problem. A manufacturer of boots plans to conduct an experiment to compare a new method of waterproofing to the current method. The appearance of the boots is not changed by either method. The company recruits 100 volunteers in Seattle, where it rains frequently, to wear the boots as they normally would for 6 months. At the end of the 6 months, the boots will be returned to the company to be evaluated for water damage. So the first thing to look at is what are the explanatory variable and the response variable. Well, the explanatory variable is method of waterproofing, either old method or new method. The response variable is the amount of water damage on the boot. You can get both of those from the content of the problem. So the first question that's asked that we must think about as we think about the design of this problem, and this isn't really one of the questions that was asked, but something we need to think about in order to answer the questions. What other variables might affect the response variable, the amount of water damage on the boot, other than the method of waterproofing, the explanatory variable? Well, some of the things that the class came up with were obviously how bad the weather was. Perhaps the body weight of the person might affect the amount of wear, the amount of time the boots are worn outside, where the boots are worn, maybe based on your hobbies or your type of job. So there's a lot of variation that could explain amount of water damage other than the method of waterproofing. And as we saw in a previous problem, let me find this here. In this particular problem, we were looking at SAT and the different ways to prepare for an SAT, whether you took the online prep course or the classroom prep course. Remember, in our original results, we saw quite a lot of variability in the results for both the online and the classroom course. And even though the online course looked like it was slightly better, it was kind of hard to tell because of all the variability. But when we took into account the variability due to what level of math they had taken, and we blocked for that, and then we basically looked at only how much they improved or went down within each block, we saw a much more clear difference between the online class and the classroom prep. So when we look at the purpose of blocking here, it says the goal of the purpose of a way to design experiments. It says the goal of the researcher is always to reduce unwanted sources of variation as much as possible so that the effect of the treatments on the response variable can be seen clearly. So we saw that after we did the blocking by classroom, we could see the difference more clearly in the results. How can we design the study to reduce as much unwanted variation as possible? So here there's all these kind of variables. One possibility is to block in some way. Perhaps blocking by type of job. People with indoor jobs being in one block, people with outdoor jobs being in another block. And then we would randomly assign subjects within each of those groups, some to use the new method of waterproofing, some to use the old, and then compare only the indoor to the indoor and the outdoor to the outdoor. Another possible blocking would be by their method of transportation, the people who walk to work versus the people who ride a bus or take a car, because that would affect the amount of water damage on the boots probably as well. But there is actually a better way that reduces almost all of the unwanted variation. So you might want to think about what that is and see if you can figure it out before I do the big reveal here. It's have each individual wear both types of waterproofing. This could be done one of two ways. Either they could wear one type of waterproof boots for 3 months and then switch and wear the other pair for another 3 months, or they could wear one method on each foot. Now, it's important, though, that randomization is still used within the experiment to randomly assign treatments. But how do you randomly assign treatments if one person is wearing both types? Well, with method number 1, you would randomly assign which method is worn first. Do they do the old method at the first 3 months or the new method in the first 3 months and then switch? Here we would randomly assign which foot gets which method. Now why is that important? In the first example, let's say, for example, everybody wore the old waterproofing method from January through January, February, and March, those 3 months, and then they wore the new method in April, May, and June. Well, and let's say the new method showed less water damage. Well, how do we know whether the less water damage was due to the time of year and having maybe less bad weather, or it was due to the waterproofing? So we just introduced a confounding variable. The weather varies from the first 3 months of the year to the second 3 months of the year, and the waterproofing method varies from one group to the other, and we don't know whether it was the change in waterproofing method or the change in weather that made the change in the water damage. So we need to randomly assign some of our subjects to wear the new method the first 3 months and some to wear the new method the second 3 months, so that we have a better comparison. However, there's still going to be a lot of variability due to the weather here. So to reduce even more variability, let's do one method on each foot. Then we need to randomly assign which foot gets which method. Now this is not as obvious. We don't necessarily know that there would be a problem with everybody wearing the left foot with the old method and the right foot with the new method, for example, but it could be that people might end up stepping in puddles more often or less often with their dominant foot. Maybe if they walk on a certain road or sidewalk a lot, that there tend to be more puddles on one side than the other. We don't really know all those types of variables, so it's better, because we don't know what might end up being a confounding variable, we should randomly assign so that there's an equal, approximately equal number of people wearing the new method on their left foot and the new method on their right foot. And then when we make comparisons, we're only comparing we're comparing the boots within one person. So like, how much difference is there in damage between the left foot and the right foot? How much difference is in damage between the first 3 months and the second 3 months? So we're not comparing individuals to each other, which introduces all kinds of other variation. We're just comparing individuals to themselves within each block. This is actually known as a matched pairs design. It's a special block of size 2, which is actually the answer towards the bottom here. The second question is, could this study be double blind, and what is the purpose of blinding anyway? So let's actually define what double blind means. A study is double blind if both of the following are true. If only one of these following two things are true, it's called single blind. Nobody involved in the treatments, that's both the subjects, people receiving the treatments, and people administering the treatments, for example, a nurse giving medicine or something, knows which subject is receiving which treatment. This is important because even people administering the treatments might inadvertently let the subjects know which treatment they're having, or maybe they might treat subjects differently based on which treatment they're getting, for example. So nobody should know. And I have kind of a funny cartoon about that, which I will show you. Here's the cartoon. It says, "Good morning, here's your placebo. I mean medicine. Well, I'm fired." This is the subject getting the medicine, who obviously didn't know which one she was getting, but the person administering the medicine, this nurse in this case, knew that she was getting a placebo and inadvertently let it slip that she was getting the placebo. So the question is this experiment single blind, double blind, or neither? Well, we don't actually know if it's double blind or not, because double blind means that the person evaluating the treatment also doesn't know which subject is in which group, and we don't know anything about that. But this isn't even single blind, because everybody involved in the treatment, both those receiving the treatment and those administering the treatments, need to be blinded. So this wasn't even single blind because of the nurse's knowledge of the subject getting a placebo. Okay, so down here again. Secondly, those evaluating the results of the experiment don't know which subject received which treatment. So let's think about this the medicine example that we just looked at with the cartoon. When doctors evaluate the results of maybe a clinical trial about a medicine, they have to evaluate the subject's symptoms. Well, symptoms aren't always clear-cut, so we wouldn't want the doctor to have some sort of bias based on his or her knowledge of which treatment the patient had received. For example, if they knew that the treatment that the patient had received was the placebo, they would perhaps evaluate their symptoms differently than if they knew they had gotten an actual medicine. So it's best for the doctor, also the person evaluating, in that case a doctor, to not know. So the question is, could this experiment be double-blind? So is it possible that both the people wearing the boots and the people evaluating the boots for water damage both don't know which boot is which? And yes, that is true. That is very possible. Both people wearing the boots and those evaluating the water damage do not have to know which boot is which. And you might think, well, how is it possible that nobody knows which boot is which? Well, that's not really the case. There is somebody who knows which boot is which. There's the researcher who is in the background. The researcher randomly assigns which, for example, if they're going to do a left foot, right foot type of an experiment, they number all their patients, and they randomly assign some numbers to get the left boot new method and some people to get the right boot new method. They pack the boots in the boxes accordingly and label them with the person's name, and the people getting the box of boots, people handing out the boxes, the people getting the boxes, they don't know which boot is which. They just know that this box goes to this person. And then the evaluators get the boxes of boots after the people have worn them, and they do their water damage assessment, and they write down the results, and then the boxes go back to the researcher who knows which one is which, and then he can analyze the results. So there's a person in the background who knows which is which, but nobody else involved in the experiment needs to know. So what's the purpose of this? The purpose of blinding is to eliminate potential bias. Knowledge of who has which treatment might affect the way the subjects responded with treatment, how others involved in the administration of the experiment treat the subjects, or how people evaluate the results. So in order to eliminate that bias, we want to blind. Now, as I mentioned before, this type of design is called a matched pairs design. It's a special type of blocking with blocks of size 2. For example, the same person gets both treatments, so both the 2 feet or the 2 arms or the 2 times that they get the 2 treatments are the 2 in the block. And then you have to randomly assign which foot or which arm or which time they get the different treatments. Twins or people with similar characteristics are sometimes put in a block with each other. So it's not just like the 2 arms of one person, but it could be 2 identical twins, or 2 people that are both the same age and the same gender, for example, could be in a block together. Treatments still must be randomly assigned within each block of 2. Otherwise, you risk having a confounding variable.